So now we're going to have a look at three-dimensional trigonometry. Now, often when you're doing 3D trig, it's really hard to get your head around the picture. So I find it useful to redraw the faces of the shape in 2 dimensions, and then I can just see a nice 2-dimensional shape. Sometimes there might be triangles that aren't actually in the diagram that you need to draw. So, all right, how do you find the angle between a line and a plane? So for this example, we've got a cone. We're told its diameter is 18, slant height of 15. It wants to find the angle the curved surface area makes with the base. So first thing we do is we drop a perpendicular from any point on the line down to the plane. Now, for the purposes of this, because we've got the slant height, in the cross-section that I've drawn there, the slant height is like a line, and we're finding the angle with the plane, which is the circle on the base. So we drop that line down until it meets the plane. Now, we've already drawn the diameter in, so we can see there's our right-angled triangle. The base of the right-angled triangle is 9. Theta is the angle we wish to find. That will be the angle between the line and the plane. So, all right, cosine theta is 9 on 15. The angle turns out to be 53 degrees. Well, what about if you have to find it between 2 planes? So we've got a tetrahedron. So all the sides are equal. In this case, we've just called them A. We have to find the angle between 2 adjacent faces. So from a point on the line of intersection of those 2 planes, we will draw perpendiculars from the point on the plane. Now you can put that point anywhere. So for this example, I'm going to find the angle between the side ABC and BCD. Now I could put the perpendicular from anywhere, but it makes sense for this question to draw it directly under the vertex. So in other words, the perpendicular height of that particular face. So E is the point that it meets on BC. But now I'll also draw a perpendicular from E on the face BCD. Now that angle I've marked in theta would end up being the angle between the 2 planes, or the 2 faces in this case. Redrawing that in 2 dimensions makes life a little bit easier. So what do we know? We know the length of AD is A, and theta is the angle we wish to find. Well, I can find the length of AE, because if I now look at the triangle ABC, just that particular triangle, each of those sides are equilateral triangles. So I know that angle is 60 degrees. I could use trig, or I'll just use the fact that I know the ratio of the triangle is 1 to root 3. It's our 30-60 triangle. The sides are in the ratio 1 to root 3. So AE must be A root 3 on 2. Now I'm going to have to use the cosine rule. So hopefully you remember that one. If not, don't worry, we'll look at the cosine rule a bit later to solve the problem. So 3a squared on 4 plus 3a squared on 4, because AE and DE would be the same length, minus a squared over 2 times a root 3 on 2 times a root 3 on 2, all tidies up that cos theta is 1/3. So the angle between the 2 is 70 degrees 32. Here's an HSC question. So we have a surveyor there at the point A, and they're due south of the tower OT. They've told us the height's H, and the angle of elevation is 45 degrees. Our surveyor now turns and walks 100 metres east to another point B, and again has a look at the tower, but this time the angle of elevation is 30 degrees. The first thing we have to do is find the length of OB in terms of H. I'm going to use a triangle that contains that side OB, so OBT. So I know OT is H, and I also know that that angle is 30 degrees. So a bit of trig, OB over H is tan 60, so OB is H tan 60. The reason I use tan 60 rather than the cotan of 30 is because we don't have a cotan button on our calculator, so I'm just sticking with the one where we have that button on the calculator. We want to show that H is 50 root 2. So another triangle I'm going to use. We know the triangle AOT, again, the height is H, but this time it's a 45 degree triangle, but this time it's a 45 degree right angle triangle. In other words, it's isosceles. So therefore AO is also H, I know AO is H. Now having a look at the triangle OAB, and remember we found OB is H tan 60. Pythagoras from there, H squared plus 100 squared is H squared tan squared 60. Playing around with that, eventually we get that H is 100 on root 2, which of course simplifies to be 50 root 2. Next bit of the question is we have to find the bearing of B from the base of the tower. So let's draw that triangle in, OAB, but I'll place the compass at O because that's the base of the tower. We found that OA is 50 root 2. We know AB is 100. The angle we want to find, the bearing, is that NOB. So if I first of all find AOB, and that's going to be the tan of that angle is 100 over 50 root 2. So AOB ends up being 54 degrees 44. So our bearing will be 180 minus that. So 125 degrees, 16 minutes. Okay, so 6C will be playing around with our three-dimensional trig problems. But as I say, you'll find it easier if you try and redraw the triangles or any shape in 2 dimensions first.